I'm going to talk to you about one of the two hot topics in lighting today. The first, obviously, is light-emitting diodes, LEDs. It's the first lighting that if you ask someone on the street, they'll actually probably know what an LED is. If you asked them 4 or 5 years ago what a CFL was, they wouldn't have known. But people are really interested in this. The other hot topic we're dealing with really now is controls. Control systems, especially wireless controls. We're doing a lot of evaluation at that at our center, and maybe next year we'll come back and talk about that. But to give you a little background on the Lighting Research Center, we're the world's largest university-based research center dedicated to lighting. We have about 40 people who do nothing but research lighting, looking at the impacts on people, on health, looking at new technologies like LEDs. And so if you have any questions as I go through, please feel free, raise your hand and shout a question at me. This is really what we're going to talk about today. We're going to go through some key terms, labeling, why LEDs, why is this technology so interesting to people, the technology itself, and then some application issues. So first of all, let's start slow. Some key terms. It's a little confusing because these are kind of new. This one you should all understand. An integral LED lamp is much like a compact fluorescent lamp. It has the LEDs, the phosphor, the electrical components, the driver, which is analogous to a ballast, all contained right in that. You screw it in and it replaces your incandescent lamp that you can no longer purchase. An LED fixture is unlike existing lighting fixtures because many LED fixtures, the LEDs are built right into the fixture. Because of thermal management concerns, the need to extract the heat from the LED, as well as other optical considerations, LEDs are less and less of a replaceable component and more of a built-in component into the light fixture, or what we call a luminaire. So if you hear a light fixture, you may have some where there are extractable components where you can put the LEDs, take them out, change them out, and other ones where they're just part of the light fixture, and when that goes through its how many ever hours, the whole fixture needs to be replaced. So as you purchase them, make sure you know what you're getting there. So for maintenance in the future, even if it's 10 or 12 or 15 years, you'll know what you or someone who takes over your job after you retire has to do. LED package, typically it's an assembly of one or more LED dies. We don't use one LED. They're very, very small. They have a relative minimal light output. So typically what the manufacturers do is package them, a number of LEDs on one, what we call a die or a package. An array is basically a bunch of these packages put together that simply, this is the component that would be replaced in your light fixture. An array of LEDs, which is then coordinated with a driver. This is, again, analogous to a ballast. LEDs are typically DC sources. There are some AC LEDs, which is basically just a way of configuring them to run on AC power. But most of them will need a driver. And these drivers, unlike ballasts, there are many, many, many different types of them. It's not like, oh, go get an instant start ballast for my fluorescent lamp 32 and they're all going to work. These drivers are typically customized to the array. So again, you're going to buy that as a package. You're not going to be able to choose your driver and choose your LEDs in a light fixture. That's going to be packaged together by the manufacturer for you. It's not like the old days. Now, there's some other terms that are a bit confusing in the LED world because everyone seems to be throwing them around. No one ever talked about testing metrics before with old technology, but with LEDs, you hear a lot from manufacturers about these. LM79 and LM80. LM stands for lighting measurement. The IES, the Illuminating Engineering Society of North America, is the professional body of lighting in the US, and they set these standards for the way products should be tested. But the way a lot of people are using them are saying that my product is LM79 certified. Well, that doesn't mean anything. All that means is that it was tested per a particular standard. So 79 is the approved method for electrical and photometric testing of light fixtures, and also lamps can be tested under this. And then LM80 is for the LEDs themselves, and all that is a lumen maintenance projection. It says this is how long my LED will keep giving light at a certain level. The information from this is used in this testing. So basically, this is where the manufacturers come up with, I'm going to have a 50,000 hour light fixture or a 35,000 hour life on my fixture, and this is its light output, and so on. So they're not certifications, they're merely a way of testing the particular luminaires according to a standard. This is the latest one, which is a technical memorandum, TM21, and this is the what they call a big word, exponential decay model. And this is telling LED manufacturers how to project the life of their LEDs. Unlike other light sources that you bought, when you used to buy a fluorescent lamp that lasted 30,000 hours, those were actually tested in a laboratory for 30,000 hours, and you knew that's the life you get. With LEDs, the equipment evolves so quickly that the longest they're typically tested for is about 6,000 hours, which can fit into a year. There's about 8,000 some hours in a year. And then what happens is the manufacturers take a portion of this 6,000 hours and they project the expected life of the LED using that. And this is the method that they use, and we'll talk about why perhaps it's not the most accurate method to use. Now, there are a couple labeling or certification programs that do exist, and they use the data from the tests. The first, and everyone knows this, is the Energy Star program. And the Energy Star label gives you two information about a product. One, that it's the most efficient product you can buy. Two, that it's the highest quality product you can buy. So this is both a quality and an efficiency standard, meaning that the products that are tested through this program must meet minimum standards for both of those things, efficiency. Now, it's a residential standard. It was meant for homes, but there are many products that kind of go into commercial buildings as well, such as downlights, under cabinet lights, coves light, accent lighting. All of these products you can get with Energy Star labels. And the thing that makes Energy Star most rigorous is the fact that all the products must be tested by an independent laboratory with the LM79 and LM80 testing, and those results are then given to Energy Star. They're reviewed by experts, and the products are not certified unless they meet minimum qualifications. So it's not just that they're tested, but that the test results from the independent laboratory meet minimum standards for quality and life. And so when you look at the Energy Star label, if you have two products in front of you, one is labeled Energy Star, one not, the Energy Star is certainly going to give you the better quality. Now, there are many, many product categories that Energy Star doesn't cover. For some reason, the US EPA has decided that they don't really want to get into commercial lighting, that they kind of want to keep it residential. And so an organization called the Downlights Consortium, and this is a consortium or a group of energy efficiency organizations, state agencies, utilities, that all kind of joined together, and they said, okay, we're going to create some standards for some of these product categories that don't exist. So fluorescent troughers, outdoor lighting, I'll show you at the end of the talk if we get to it. All of the different product categories. And this, again, they review the testing standards, but it's a little less rigorous. The testing does not have to be done by an independent laboratory. They aren't reviewed by experts. They're simply reviewed, well, yes, the information is there, and so you get on the list. Also, the categories, the qualifications for the categories are not quite as rigorous as Energy Star is. But at the end of the day, if you know nothing else about a product, at least if it's on this list, you know that it has gone through some review and does meet some minimum standards. So those are the two things that we want you to look for when buying a product that you might be unfamiliar with. Because in the LED world, there are many, many new companies that are starting up. They say that in China, there are 200 companies a month that are starting up to produce LEDs or LED products. So you're going to see a lot of competition in this area, and we want to make sure you're getting quality. So why LEDs? Well, there are two types of solid-state lighting, we call it. LEDs, which are inorganic light-emitting diodes, which are made of materials such as gallium nitride is the main material. It's not a toxic material. It sounds terrible, doesn't it? And then there's light-emitting polymers, or what we call organic light-emitting diodes. And these are flat panels of light. If I come back in 5 years, we'll talk a lot about these. But right now, these are inefficient. They're not very long life. They have a lot of problems with control of moisture and humidity. Even if you keep these on the shelf in your warehouse, they start to degrade, even if you're not using them. So there's a lot of work to be done there. Cell phone displays are made of this, and if you've seen the new LG TV that is a curved television, it's gorgeous. That's an OLED TV. Fantastic color quality with this, and a very, very thin profile. So you can imagine in the future ceiling and wall materials that'll be able to be rolled out that will actually be light. And it's a very, very interesting technology, but not one we're ready for right now. When we look at LEDs, why are we so interested? Well, when you look at the maximum efficacy, the lumens per watts, from all these existing technologies, from fluorescent, it can go up to 120. It's almost there. It's not going to get any better. High intensity discharge, these are your metal halide and your high pressure sodium sources. They have a potential to get to that, but you're never going to see that because of the cost involved in getting there. When we look at LEDs, we have a projected efficacy that could go up above 300 lumens per watt. That's 3 times the efficacy of our current lighting that we use. Fluorescent is the main light source used. It typically, once it's installed, well less than 100 lumens per watt. So we're going to see that. Now, where are we now? If you look at 2014, these are the efficacies that we see. We see about, for cool white, something about LEDs, the cooler color temperature light sources, if you know what I mean by that, the whiter light sources above 4100 Kelvin, and that's a description of the whiteness of the light source for those of you who are not familiar with that. They are typically more efficient because they rely more on the LED and less on the phosphor. So those are up almost to 200 lumens per watt by now, and then we see the warm whites a little bit under that, about 160 to 180 lumens per watt. But still, from an efficacy standpoint, that's much better than existing sources. By 2016 or so, we will see them cross the 200 lumens per watt mark, which makes it twice as efficient. So imagine that if you have fluorescent lighting in your building and you were to replace it all with the very highest quality LEDs, you could potentially cut the cost of that by 50%. And that's huge. Never before have we had a technology where we could really cut in half the energy use of our lighting. So that's really the interest in this, coupled with the life. So if you look at the global market, this is the fluorescent is still growing and will continue to grow. Solid state lighting will also continue to grow, and incandescent and other sources will really, the market will shrink for those. So we see a potential for energy savings, much lower replacement costs because they're going to last longer. They're very rugged and durable. It's not a glass envelope that's going to break when you drop it. You can play basketball with an LED. In fact, I've seen some basketballs with LEDs in them. Unique lighting solutions. It's easy to modulate their intensity, in other words, to dim them up and down. And we can also, with certain technologies, change their color, which is interesting to some people. Potential for low ultraviolet and infrared radiation. If you're an art museum, that's important to you. And then there is no mercury, which in this world where we're trying to eliminate all of the hazardous materials from our buildings, that's really important to people. They don't want mercury in their buildings. They don't want to pay the recycling or recapture costs for that. And so that is something that is important to a lot of people. So how do we make white light with an LED? Well, there's no such thing as a white LED. LEDs can only produce light in very narrow wavelengths along the electromagnetic spectrum. So if you look at the spectrum from 380 nanometers to 780 nanometers, that's the electromagnetic spectrum of light. We associate this kind of with purple and blue and then green in the middle and red toward the end. That's the emission spectrum of an LED. There's the blue. So it's a blue LED that's coated with a phosphor, a very long phosphor. In other words, it covers a lot of the spectrum. It's a yellow phosphor. Those mixed together produce a very high quality white light, meaning that it's a very pure white and it has very good color characteristics. It will render colors very well. The other way to produce white light is to mix the 3 colors of LED. Now that's actually the more efficient way to do it. This is more efficient than this. The problem with a mixed color system where you're mixing a blue, a green, and a red LED is that it's very difficult to keep those consistent. They're made of different materials that degrade at different rates. The red, for instance, degrades much more quickly, and you need more of that. So your perfect white light that you've created in the lab, after it's in use for a couple thousand hours, changes color, and that's not very good. Now, what this is used for is all those color changing capacities. So when you see a building as you drive by that changes from red to green to blue, that's what's being used, and that's a great application for that. But this is really what we're talking about when we talk about LEDs. Now, they can come in very, very many correlated color temperatures. So this would be analogous to incandescent light, that warm yellowish light, right up to a very, very bluish white light or above, even 6500 K or more for specialized application. Now, typically, you're not going to use this in interior. That's exterior lighting, because our eye actually is more tuned to the cooler spectrums at night. We see better under it, and so it actually gives us improved safety and efficiency to use those temperatures outside during the nighttime. For interior applications, you're certainly going to see, much like fluorescent lights, 3500 Kelvin, 4100 Kelvin. Those are the neutral white lights, 41 being really the purest white light, although people do tend to like a little bit warmer 35. This is going to be very confusing to people, the CIE XY values. To make this very simple, this is the CIE color diagram. The CIE is the world body of lighting. It's the Commission Internationale de Éclairage. It's a French agency, the international body of lighting. And this is the diagram that if you plotted all the colors of light, you would get this kind of U shape. And everything on the boundary is very saturated. Right in the middle is where white light exists. And if you can get a light source that matches this boundary very well, it means that it's a pure white light. It won't have tint. People do not like tint to their light. With compact fluorescent lamps, to try to make them more efficient, they had to move them up a little bit off this boundary. And what happened then? They turned green. Or to get them warmer, they had to move them down. And what happened then? They turned pink. So you would buy 2 or 3 of these, you'd put them in your lamps at home, they'd be pink or they'd be green, people would hate them. And that is where fluorescent light has really gotten its nobody looks good under fluorescent light name. With LEDs, they're right along this boundary. They have a very pure white light. They're not going to have a tint, which is excellent for light sources, for people really attuned to that. And they have very good color rendering properties, which mean that colors will look both natural as well as vivid. What other light sources can't do, other light sources like the phosphors used in fluorescent lamps or incandescent lamps can make things look relatively natural, but they can't really bring out the colors of items. There are 2 dimensions to color. One is naturalness, the other vividness. And what the LEDs can do, and the reason why they're used in televisions and those kind of things, is that they can really make those colors pop. In fact, you could make them overly saturated, but with lighting we don't do that. So as we see the technology develop, we're going to have more light output per device, so fewer LEDs, lowering the cost, higher efficacy, better color properties, and longer life. That's really what the manufacturers are looking at right now. Once they hit that 200 lumen per watt range, you're not going to see the efficacy increase too much above that, maybe to 220, maybe up to 250 for some really aggressive manufacturers. But basically by that time, when you've surpassed twice the efficiency of other sources, what they're going to start working on are these quality factors to really make this a good, consistent, cost-effective light source. Much above 250, it's going to cost many millions of dollars of research to get those chips to get that light output. There's a few problems right now with LED technology. One is called the green gap. It's a problem with the material getting emission in that wavelength, as well as imperfections, as well as light extraction. It's hard to get the light out of these chips. About 50% gets stuck in the package. We have a big interest in arrays, so we're going to see more and more of these high-power arrays. They can either be individual LEDs masked on a chip, or sometimes they put the phosphor on a disk. Again, that doesn't mean too much to you, except This is going to create problems a little bit with thermal management because the chips in the middle are going to be a lot hotter than the chips on the edge. And that's a problem in management. Heat is the enemy of an LED, and so we may see some problems from that. When we talk about efficacy with LEDs, we talk about efficacy is, as opposed to efficiency, efficacy is measuring two different things, like miles per gallon. It shouldn't be called efficiency, that actually should be called efficacy. Efficiency is when you measure like watts in, watts out. So when we talk about efficacy, it's the light output of an LED over its input power. Now, what you care about really is the LED fixture efficacy. So this would be from a screw-in replacement lamp or from an entire fixture that you buy. It's a novel way of doing it. Light output of the luminaire and total input luminaire power. The way we used to do it with lighting is to say, okay, you have a lamp with a certain efficacy, a fluorescent lamp that is 98 lumens per watt. You then put it with a ballast, and you have to take into that account, and so you had to do that calculation as well with the ballast factor, and you said, okay, now my system efficacy is only 89 lumens per watt. Then you would put it in your luminaire, your light fixture, and your light fixture would have an efficiency of 80%. So then your 89 lumens per watt just took another hit, and you went down to what? 68 lumens per watt. But you had to make all of those calculations and figure that out depending on the luminaire that you were buying. With LEDs, they said, we're going to simplify that. When the consumer buys the product, they're going to know exactly the light they get out for the power they get in. And so it's a simplified way of saying, when you buy my fixture, you're going to know that you get 2,500 lumens and that the total input power of that is 28 watts or whatever it is for my fixture. So it's a simplified way of doing it. Now, when we talked a little bit about efficacies, in 2013, cool white surpassed 160. Warm whites were still at about 120. Next year, you're going to see them get up very close to 200, and I would not be surprised if some manufacturers are going to get over that by that time. But there's a big but with that. You're not going to get 190 lumens per watt. That's the problem with this technology, and everyone's saying, oh, wow, it's 200 lumens per watt. Because the system is kind of complicated. There's a heat sink, which manages the thermal. Typically, it's an aluminum material of some kind. There's the housing, there's the driver, there's a circuit board, there's an array, there's optical lenses over the arrays, and then there's some kind of diffuser usually over the whole system. Now, when we look at that, our LEDs are at 100% efficiency. Let's say they're 200 lumens per watt. Well, we take a 15% hit on optical loss. When they encapsulate that LED, which they have to do to make it operate, you lose about 15% of that 200 lumens per watt. Then when we take a thermal loss, there's no way to operate the LEDs in this fixture at their exact temperature. Their exact perfect temperature is about 35 degrees centigrade, which is about 90 degrees Fahrenheit. Now, that would be great, but there's no way once you put this thing in a ceiling, you're going to get that exact temperature. So for its thermal condition, you're going to take an additional loss of about 15%. And then unfortunately, these drivers, which convert AC to DC, are very inefficient. So at every fixture, you're going to take an additional 15% loss. So your system efficacy, the whole fixture, is going to be about 60% of what you see LED efficacy is. So if you have a 200 lumen per watt LED, you can expect that you're going to take about a 40% loss on that when you actually buy it as a system. And so when we look at efficacies of actual products, they're not in the 200 lumen per watt range. They typically are in the 100, 110. I think there's one troffer you can buy that is about 114 lumens per watt or almost 120 lumens per watt. But that's the best you're going to do this year when you get the actual product. You have to be a little bit careful with color variation right now between LEDs as they age. So if you have an application, let's say, where you're washing a white wall with light, you have to be careful that maybe LEDs might not be what you want to use for that right now. I would say 2 years from now, this will be solved. There's a lot of work being done. This, again, is the black body. Right now, these are the color boundaries. In other words, this is the amount of variance, this big square, that's allowed between individual chips in a bin. What we're recommending through programs that we're doing to the industry is to tighten that dramatically to the point where people will not be able to notice the difference. And once the industry adopts that, it again adds a little cost for them. You'll see that the color variations will improve. So what is lamp life for an LED? This is interesting because it's new. Again, when you bought a 30,000 hour fluorescent lamp, everyone thought it meant that every fluorescent lamp would last 30,000 hours, right? It didn't mean that. What it meant is that they tested a large group of lamps, and when half of them failed, they said, boom, 30,000 hours. It meant that if you put all these lamps in your building, at 30,000 hours, half of them would be burned out. But at least it was a testing metric, and it was for life. Now with LEDs, they kind of never die. They stay around forever, but their light output goes down. So they said, well, how can we rate life for a product that really doesn't die? They said, okay, well, once we lose 30% of the light, it's really no longer useful. It's not a useful product. It's 30% diminished from what it should be giving us. That's what we're going to call life. And so when they made up the LM80 specs, they said, okay, we're going to test these things at a particular temperature, and when they reach this degradation, or when we project they will reach this degradation, that's what we're going to call life. So it's called L70 typically, you'll hear, and it's a 30% reduction in light output. And that basically is when your life spec is. Now, does that mean your LEDs are going to be burned out? Maybe not, maybe. So in critical applications where your light level is very important, it's an industrial facility and you're very, very careful with the light levels in your system, if the light bulbs don't burn out over your head, are you ever going to change them? Well, no, because you're going to get used to the light degradation. It happens so slowly, you might get used to it. So we're going to have to monitor that and be careful, because no little red light is going to flash and tell you, change me, change me. You're going to have to be careful with that. And that's happening with traffic signals. And the first generation of traffic signals right now have degraded to the point where they no longer meet the requirements. Can you imagine the lawsuits at the intersections where the LEDs don't meet the requirements? Because a very smart lawyer will have his luminance meter out there, he'll be measuring that, and he'll say, oh, these have degraded below the requirement, and that's why my, my client got hit, and I want $1 million for that. So certainly that's a very important application, and they've kind of solved that problem with a little red flashing light that tells the maintenance guys, change me, change me. But with regular products, they're not doing that, so you have to think about that as one of your things. Now, the other thing is that all products are not created equal. Some degrade very quickly, others last for a very, very long time. And you don't know what you're getting. Because, again, it's done on projections. I test them for about 6,000 hours, and then I project what they will do, and that projection is not always the case. So with lifetime projections, you have to be a little careful. And the other thing is that it's only the LED that's included in that life. Remember all those other components, the optical components, the driver, the circuitry, all the interface materials between all those pieces? That has nothing to do with the life metric. So what's going to fail first? I'll tell you, it's not the LED. When we've taken apart traffic signals and we've tested the LEDs, they all worked. You know what failed? The circuitry behind it, that circuit board that held them all together, and all those interface materials. Imagine a light going on and off and on and off and on and off. It heats up, it cools down, it heats up, it cools down. What happens to metal when it goes through those conditions thousands and thousands of times? You get fatigue, it starts to break down. All those interface materials are what's breaking down. And so the industry now really needs a better metric for life. They really do. Right now, the lumen maintenance one is all they have, but you have to be careful. And so what are we advising consumers to do? Get a warranty. If you say your product's going to last 50,000 hours, I want a 5-year warranty on that product. I want to know that if that product burns out, you're going to replace it no matter what went wrong, unless it was my fault because I dropped it in a pool of water or something. And in some cases for outdoor lighting, I've seen companies give 10-year warranties. Now, you have to be careful what that warranty covers. It may only cover the LED. So again, you have to read the fine print. But a warranty is going to be your best protection right now. If you overheat these LEDs, they will diminish in life dramatically. LED manufacturers set a maximum junction temperature, and typically that's relatively high. It's about 90 degrees C, and we'll see some actual applications where maybe we actually get to that. For every 1 or 2 degrees over that, you could actually be cutting the life of that LED in half. So you have to be careful that when you install these LEDs, you put them up in your ceiling plenum or wherever you're going to put them, you have to think about the thermal conditions there. Also current. You have to make sure that the current is maintained at optimum levels. Now that's the driver's job, it's not your job. But what again you need to know is that sometimes the driver doesn't do its job well, and that can be a problem. So think about all of the pieces, the circuit board, the optics, the thermal interface materials. That really is what we're looking at for life. And we're doing a lot of testing now at the Lighting Research Center, trying to come up with a better metric for life. We've tested things for 3 years under various conditions, and we think we've got a better metric for an accelerated life test for the product itself. And hopefully you'll see the industry adopt that. It takes the industry a while to adopt things. So when we think about application issues, we think about replacements. There are a lot of replacement now, especially for lamps that you could put in downlights that you could put anywhere. But think about where you're putting them. You've got this nice LED replacement for this halogen lamp. These are called MR16s, small. You see them a lot in retail, high-end hotels, those kind of things. Very efficient, extremely efficient in long life replacement. These things didn't last very long. They would die in 1,000 hours, and they're very inefficient. Great thing to do. Put it in this application. This is an IC rated, which typically is used in residential or any ceiling that has insulation. Now, if I stick this LED with all of its thermal components behind it into this metal box, where's the heat going to go? Nowhere. It's going to stay in that metal box, and it's going to heat up, and it's going to heat up, and it's going to heat up. And this LED that was rated to last 30 or 40,000 hours is going to last about half that time. Now, if I put this in this application with an open back, this is, typical track light where it's hanging in space. Fantastic application. That convection is working, it's cooling that lamp, it's going to last for a long time. Again, an enclosed fixture, not as good. So think about when you're doing lamp replacements, where are you putting that product that's supposed to last that long, and how are the conditions going to affect its life? If it's in an insulated ceiling and it's supposed to conduct the heat away, it's not going to do it. Now, what some manufacturers are doing, if you've seen the latest replacements for downlights, the kind of pop-in replacements, they have a nice trim. They're all like white metal now with a nice trim. They're actually convecting the heat to the outside via that trim, and that actually is working pretty well. So they've thought about this in some applications, but you have to think about it too. Now, this gives you an idea of what the heat is in some typical applications. So 90 degrees C is really kind of the death knell of an LED product. If it gets above that, you're going to have some problems. So what we did is we tested them in table lamps, and they were fine. We tested these replacement lamps in an enclosed globe where there was only one, and they did reach just above that 90 degrees C when you got to like the 17 watt version, which is like the 60 watt replacement version. Now, when you enclosed it in this type of a luminaire and there was only one, again, a little bit above, but this is the big enemy, and this has been a big problem in residential replacements, where you have more than one LED lamp in a fixture, and you're putting them all in there. Look at the temperatures, almost 120 degrees C. Now, I'm not good at calculating, but that is a tremendously hot environment, and your LEDs are not going to last very long. And actually, we've seen some LED products. We had them in the lab. We put 3. The first thing that happens is they change funky colors. They turned pink and green and all funny colors. It was kind of interesting, but not if you just paid, $20 for your light bulb. And then they died. So that is a concern that we have to have, that if you're going to mass multiple of these lamps in one application, even if they're like the linear fluorescent replacement lamps, heat is very important for those too. So if you're replacing those in enclosed troughers, or you've got the screw-in replacements, they make them now for HID lamps. If it's in an enclosed fixture, you're going to be getting these temperatures. So you have to be careful with that. Now dimming. I told you that intensity is very easy to manipulate with LEDs, and it is. If you use the right electronic dimming system, it's very easy to make these dim exactly as you want them to. The problem is that most people are trying to do the dimming on traditional technologies. There's no definition of what dimming should be right now in the industry or how things should be dimmed. Again, it's not standardized yet. So what's happening with a lot of these products is you get these funky, what we call dimming profiles. So this is 0 to 100% light output. And what you'd actually like to see is something like this blue line. You'd like to see that when you moved your dimmer, the light output went up in a nice arc, and that's what we expect. Now, what we're getting, though, are things like this, where nothing happens for a while, and then all of a sudden it pops on. They actually call it pop-on. And that's actually what happened there. What happened here is it went up to here and finally popped on. And these are some other dimming profiles with the same problems, where you're dimming down and you have all different funky things happening with the lamp. People aren't liking that. And the reason for that is that the triac dimmers that are used are not really meant. They basically chop the AC wave. And that was great for an AC light source, but it's not great for a DC light source with an electronic driver. And so what's happening is there's a lot of incompatibility between existing drivers and replacement lamps or new products. So you really have to check with the light fixture manufacturer to see which dimmers will work with each product. Now, that seems pretty simple. What happens when you buy a fixture is they'll give you this list of like 5 or 6 or 7 different companies and model numbers that'll work with their products. Now, we did testing on those, and in some cases they did, and in some cases they really didn't work all that well. So again, it may be something you want to try out. The bigger problem is, when you're doing a job, you typically have 3 or 4 or 5 types of light fixtures in it. If they all have dimmers, and all the dimmers are different, that's a headache for installation. Think about that installer. Do you think he's really reading the spec sheets and say, this dimmer goes with this light fixture? No. He's, oh, this is a dimmer. And he puts it in the wall, and he doesn't know what light fixture it's dimming. So you have to be careful. We've seen some jobs where there were 5 different control technologies for each of the different types of light fixtures. So it becomes a little more complicated, one more thing you have to pay attention to, either in retrofit or in new construction. It's worthwhile, though, because if you do follow the instructions, typically it will work. The other thing is that when you're dimming just a couple fixtures, 1 or 2, you're going to see some variability in how well that works. These products, because they're so low wattage, and the controls are used to higher wattages, they're used to 30, 40 watts, and some of these fixtures are 11 watts. They have a difficult time controlling a little bit of wattage. So once you get to 4, then typically you're okay. Between 4 and 10 and 12, it's fine. But when you're in just dimming a few, like you just want to retrofit the downlights in your kitchen and you only have 3, you may have to play a little bit, make sure you can bring it back. Sometimes in the lower ranges, if you are seeing problems, there may be some flicker, variable dimming ranges. There can be electromagnetic interference with these products because, again, you're dimming an electronic component. If it's not being done properly, you may see some EMI. Now, in someone's home, that's typically not really a concern. But if it's a critical application where that's going to be a problem for you in your building, then you have to pay attention to that. And they typically will require a minimum load. It's very difficult to dim just one little downlight with a dimmer. Now, when we look at replacements for luminaires, we can replace anything now from an under-cabinet light to right up to an entire building, industrial facility that used 400 or 600 or 800 watt metal halide or high pressure sodium lamp. So it just basically is scaling up the number of LEDs in that particular product. Some trends, downlights, it would not make sense to me to buy anything but an LED downlight. I would not buy a CFL downlight ever again. I would certainly not buy an incandescent downlight. LEDs do directional lighting better than any light source because they are a very directional light source. So it's really the optical gain that you're getting, plus an increased efficiency. When you look at CFLs, compact fluorescent lamps, which I think is what we have over our head, they're maybe 60 lumens per watt if you get a really good quality one. Now, LEDs, you can easily get even an LED replacement that's up close to 100 lumens per watt. So on efficacy alone you're saving, but it's really the optical efficiency. It's very interesting when you look at the different technologies. These are some downlight ratings that Energy Star gives. This is from last year, and we are seeing them go up above now 70 and 80 lumens per watt, both commercial and residential. So you're getting downlights at about the 80 lumen per watt out of the fixture. And again, that's not the lamp, that's out of the fixture. Input watts to out, 80 lumens per watt. With Energy Star, their requirement for commercial products is that they last at least 35,000 hours. That is the minimum requirement. Most downlights for commercial applications you'll see will have ratings of 40 and 50,000 hours. Again, that's based on a projection, but for life, that's doing very, very well. Now, this is an interesting curve. I really like this because it shows you the problem with projecting LED life. Here is about 10,000 hours, and this is the most an LED is ever tested for. Typically, it's about 6,000. Now, if you used a model and you said, wow, look how good my LED is doing, it has lost absolutely no light. In fact, this one's actually increased in light output, and that actually can happen. If I put this in a mathematical model and I project that life out when I take this little slice, what happens? Well, it projects like this. It's an exponential decay, but it projects out to here. Now, what really happens? Well, it's like Niagara Falls. At a certain point, and typically it happens just after 10,000 hours, there are things that happen within the LED, and typically it's the optical lens material that's made of an epoxy begins to yellow. And once that happens, that is bouncing light back into the chip, which is heating it up more, and also allowing less light to escape. And so that's how LEDs actually die. So sometimes these projections are not really realistic, but look for the Energy Star label. You know you're going to get at least 35,000 hours, if not more. Now, here's the big thing with LED products. System efficacy of 54 lumens per watt, and this is a replacement product. This actually now, this company has one that's over 60. Here is the typical system efficacy of a CFL downlight. Even though you were starting with a lamp that was 60 lumens per watt, when you actually put that lamp in a downlight, this is what you actually get out. And why is that? The optical efficiency of a CFL downlight is less than 50%. 50% of the light is trapped because you're taking a blob of light, this big blob, and you're trying to squeeze it through a little hole, and that just doesn't work. It's very difficult to optically control a fluorescent technology because it's a diffuse source. It was never meant to be put in a small package. We see troffer replacements, and this is very interesting because we have some troffer replacements now that you can buy for about $120, a 2x2. One company came up with it, and then 2 other companies. So now all 3 of the major luminaire manufacturers have replacement troffers that are at the low $100 range in cost and are at the efficacy range of well over 100 lumens per watt. So from a standpoint of cost and efficacy, LEDs are there. Now the thing is, fluorescent lamps have also evolved. What used to be a 20 to 30,000 hour technology is now what? 80,000 hours. All the big 3 companies have an 80,000 hour fluorescent lamp. So if you're buying LEDs for their life, and you say, okay, I'm going to replace my fixture because it's going to last for a much longer time. If all you have to do is go out and buy that 80,000 hour lamp, now it's much more expensive than your 20,000 hour fluorescent lamp, and you don't have to do anything but replace that lamp, sometimes that makes sense. You're not going to save any energy, but if maintenance was your concern, then that's an issue. But you are seeing replacements now that you can reduce the energy use by 20 to 30%. And typically in lighting, when we get to that 30% range, it's kind of the holy grail. It's where payback begins to make sense. Even if that costs more, the payback at 30% energy savings in an application where it's used 12, 14 hours a day, the payback is there. So we are getting to the point where if I did this talk last year, I would have recommended against it, but I tell you, they're getting there. Here are some of the replacement T8 lamps where you see the efficacy is up above. We see some troffers. Here's one that was 106.6 lumens per watt. I've now seen one at 110 lumens per watt. I have 5 minutes. And even the replacement lamps are getting up there. Here's one of the LED troffers, lighting facts. Oh, this was 119.5 lumens per watt. Lighting Facts is a program run by the Department of Energy that tests these products for a label. So we do see about 120 lumens per watt. And again, when you think about remember that's watts in, light out. With the fluorescent, even though you had a 90 lumen per watt lamp, you take the loss for the ballast, you take the loss for the efficiency of the luminaire, that is actually only about a high 60 to 70 lumen per watt luminaire, light fixture. Compare it to a 120 lumen per watt light fixture. You've getting close to 50% energy savings there. And I have to say, we've tested even some of the T8 lamp replacements, and they're looking really good. Again, a year ago, I would have told you no. But we just did one. I have to give a seminar in New York City on Friday, so we did a bunch of testing of these, and I was impressed with both their thermal maintenance as well as their light output and their distribution. They get the distribution right. Some of these products are really evolving. So when you're thinking of questions, what type of fixture is it? Is it going to be enclosed? Is heat going to be an issue? What's the type of installation? Is it going in a ceiling where the plenum's going to be very hot? Is the quality and quantity of life going to be sufficient? There's still manufacturers out there that are selling you a 2x2 or a 2x4 fixture replacement. This LED fixture will replace a 3-lamp fluorescent troffer. Well, a 3-lamp fluorescent troffer, even taking into account all of its efficiency, probably gives you between 6,000 and 8,000 lumens. Sometimes people are trying to sell you a 4,000 lumen replacement for that. Can you replace 6,000 with 4,000? No, unless your space is overlighted already, which it probably is. That's not an apples for apples comparison. So when someone is selling you a replacement, look at the lumen output of the replacement and compare it to the existing, because they're trying to get away with selling you ones that are don't give you as much light as what you're replacing. Is it dimmable? If so, what controls can I use? How long will it last, and what's the warranty? The replacement, that's a big thing. These are electronic components. And what happens when you buy 1,000 electronic components that you put in your building? 6 or 7% of them are going to burn out in the first year. It's just the way things are made. There's just no way around it. They call it the bathtub curve, where a few things die at first and then it levels off and everything lasts for a long time, and then you get a lot of deaths at the end. It looks like a bathtub. Well, if let's say a year from now, you have 3 fixtures that burn out, and you bought the best LED fixture, was LED fixture 105. And now all they're offering is LED fixture 205. Well, it has twice the light output in a different configuration than your 105s. You try to stick that in your ceiling, it's going to look funny. So does it mean you have to buy 10 extra fixtures? Some manufacturers are actually recommending that. But you may want to ask your manufacturer, what's your guarantee that I'm going to be able to replace this with the same thing? And then what's the cost going to be? Now, I'll quickly go through these DLC categories. Remember I talked about the Downlights Consortium list? This is a list you can go to online. There's actually, I think I put a URL on the first slide. I think Xcel will probably give you this presentation so you can find that. But all outdoor luminaires, just about everything outdoor is there. Fuel pump canopies, refrigerated case lighting, retrofit kits, 4-foot linear replacement lamps, and they have a very strict standard for these. These are basically if you just want to take out your fluorescent lamps and stick in. They actually make these that will operate right on your instant start ballast. You stick it in, and it saves about 10 watts per lamp. So now it's expensive. These can cost $30 to $40. 10 watts per lamp, you're going to say, well, maybe that's not what I want, but long life, you don't know. Linear panels, these are troffers, high bay, low bay, retrofit kits for high bay and low bay. Be very careful with those, again, for heat concerns. Aisle lighting for like warehouses, Parking garage, a lot of parking garage luminaires. That's a big application for LEDs because they can be dimmed so easily. You can step them down. Our parking garages are typically lit at full light output 24 hours a day, which they don't really need to be. But it's so hard to control other technologies that everyone said, we're just going to do that. Where with this, you can easily change that. These are some of what we consider the near-term applications. Certainly any directional or decorative lighting, outdoor lighting, under cabinet lighting. I would also put in things like troffers now, even high bay lighting as the kind of the new frontier of what's this going for. The only thing they've been unable to do with LEDs, stadium lighting. And there are a lot of companies trying for it, believe it or not, but they just can't get the beam angles right. So, when you think about LEDs, you have to think about all of the interactions in the system. It's not just lumen depreciation, so it's not just LED life. There's the array, the driver, everything else. And the LM80 standard just doesn't cover those things. So you as a consumer have to be wary. I'm certainly not telling you not to buy these products. Some people come up to me afterward and they say, oh, I was going to buy LEDs, but now I'm not going to after your talk, and I feel so bad. I'm not trying to tell you not to buy them. I'm trying to give you the information so that you're an informed consumer. The more you know, the less anybody can kind of pull the wool over your eyes. This is an excellent technology. I highly recommend it. But you need to do your homework. You need to know things more to be able to buy it. It's not just what you're used to. Industry experts expect that about anywhere from 25 to 50% of lighting sales by next year will be LEDs. Everybody is going into this technology. So I was exactly on time, wow. Or you just kind of morphed and you said, oh, he's going so slow, I'm going to be nice to him. So, all right, questions? I don't know if I have much time. Well, it's not really the same thing. UL is a safety standard. So UL testing means that it's not going to burn your house down. The Energy Star standard has to do with efficacy and quality. So UL doesn't talk about quality at all. The LED, if it's a UL rated fixture, the LED may last 2 minutes, but it won't burn your house down. So basically, there is some overlap in that they're looking at testing. When they do the UL testing, basically what they do is they put the fixture in a box, which builds heat up around the fixture. And for Energy Star, that's the recommended testing method. So what they're looking at is doing the Energy Star and UL testing at the same time, because it's really important to test these things what we call in situ. In other words, in the situation they will be it at plenum or an enclosed or an insulated ceiling. So there is some overlap, but all UL is telling you is a safety thing. That's all that is. It has nothing to do with quality, life, light output, anything like that. But good question.
Is there more degradation of the LED or electronic components for thinking?
No, it doesn't seem to affect the life of an LED. And in fact, if you dim an LED, what happens is it's running at a cooler temperature. And so it should actually extend its life. So a lot of parking garage products where you see that they're recommending that they're either dimmed or turned down, stepped down when there's no motion, their life expectancies are out to 100,000 hours, because when it's dimmed, and it's expected to be dimmed about 80% of the time. Do you know parking garages are really only occupied about 20% of the time? People park the car and they leave. Then they come back and get it at the end of the day. So dimming can actually extend the life. It could kind of be like an incandescent technology. With fluorescent, it made no difference. In fact, it could shorten the life. But with LEDs, it could extend the life, depending, again, how well that dimming is being done. So that's a good question.
You said the lens is yellow after like 10,000 hours. You just replaced the lens.
Well, it's not the lens of the fixture, it's the lens of the LED. So, you know, when you buy an LED, it has that encapsulant on it. I should have called it an encapsulant. That's a permanent part of the LED. If you take that off, the LED won't work anymore. So it's that encapsulant material. And they made it out of epoxy at first, which is bad. Now they're making it out of silicone. Now silicone's more expensive, but silicone has its own issues. Now they're trying to come up with some other materials, and they're experimenting with some glass and ceramic materials that will not yellow. But again, it adds cost. So you will see that improve. Now that we know that that's the major degradation mechanism, or a major degradation mechanism, they will be trying to fix that issue, but they have to do it and not have you pay, you know, $35 for an LED.
We've also noticed that you said it's dimmable, which I see that on a lot of the boxes, but they should say dimmable with the red dimmer.
Exactly. Yeah, the Natural Resources Defense Council, which does a lot of work in trying to encourage the use of energy efficiency product, that was their main thing this year. They said, you know, they bought like 15 different lamps, and they said they all say dimmable, and they all have in fine print, you know, this is what you need to do, or you have to go online to find what dimmers to use. And they said, you know, for the American consumer, that doesn't cut it. You people have to be better. And so they're trying to put some literature in with the lamps. It's tough. It's a tough issue. I would say it's going to be solved. NEMA, the National Electrical Manufacturers Association, is coming up with a standard. And so there will be a standard dimming for LED products so that all the products are made to work on a particular type of dimmer. Then all the manufacturers will make that dimmer and it'll be solved. But right now, that's not the case. Oh, okay. Yeah. You can ask me after.
Anyway, I was just going to ask if there's a quality standard for consistency in like office fixtures. Some facilities that are in, you get a whole bunch from the same manufacturer, but one will be slightly different than the next, to the next, to the next, and they don't look very good.
Yeah, it doesn't. And the qualified product list, the DLC qualified product list, is trying to address that. It's not perfect. Again, this is a new technology. I just saw that. We just did a huge a grocery store in Albany, one of these newfangled ones with restaurants in it and everything. It's probably like a Whole Foods, which we don't have either. You're probably thinking newfangled. We have those already. But in Albany, New York, we don't have those. And that was an issue. We saw that a lot with all the aisles being lit. You could see, ooh, that looked really bad. And actually, it was a wiring thing. It was the way they were wired in. It was not the fixture product, the product itself. So there's a number of interactions going on there. But the qualified product list is trying to address that so the light output of these is standardized. Because when they say it gives you 2,500 lumens, one may give you 2,500, one 2,800, one 2,000. And so there is a little variability which people can notice. But a good quality product's not going to do that. Someone, you know, is probably trying to save money buying those troffers. So I think we're out of time. Thank you.